Yeah, thanks for the invitation. I'm really excited to be here. It's a really great group of people. Um, yeah, and because I moved to Canada, Tice has to say North American session. So I'm at the University of Waterloo in physics and the Institute for Quantum Computing. And what I want to tell you about today is some work that we've done in collaboration with Wolfgang Ketterle at MIT on sort of Feshbach resonances and how they connect to ultracold chemistry and can teach us some new things about what's going on in chemical reactions. So I don't think I actually need to tell anyone here about Feshbach resonances, but I want to just give a quick reminder about atomic Feshbach resonances before we get into the fun ones. But we need these atomic resonances to make our molecules, so that's important. So we're looking at triplet sodium lithium. So in the rho vibrational ground state of the triplet potential, the singlet potential is here for reference, and by here I mean somewhere on the floor below us. So the triplet state is a much shallower potential, but still very stable molecule. Not a particularly large dipole moment, but it's got two dipole moments, magnetic and electric both. So we follow this sort of standard prescription that people have already mentioned, starting from Debbie Jin and Junier's group. A magnetic field sweep to produce this weakly bound Feshbach Feshbach molecule. And again, I'm just going to quickly run through because I know this is a well-worn path here. So when we have two states that cross as a function of some control parameter, in our case the magnetic field, if there's any coupling between them, we open this avoided crossing. And so now, I've got sort of the two different molecular potentials with a small shift due to the opposite magnetic moments of the free atoms versus the molecular state. And as we sweep the magnetic field, we bring a bound state into resonance at threshold with our collision, with our colliding pair. And we can coherently transfer from atoms to molecules. Of course, this is step one. And then through a Stirac process, we produce the rho vibrational ground state of these triplet sodium lithium molecules. So what I want to talk about for the rest of the talk, though, is chemistry. And particularly since this is Ultracold Molecules Conference, ultracold chemistry. I left some space there because what I really want to hammer on is this idea of coherence in a chemical reaction. Okay, so talking about coherence in the short-range dynamics of a chemical reaction. And anytime I talk about chemistry, I sort of give this standard disclaimer. With time, I think maybe I can retire this slide, but not quite yet. So what do I mean by chemistry? Well, I mean scattering, right? Don't tell the chemist I said that. I keep trying to make friends with chemists, and I think statements like that are hurting me. But so we have three parts to a reaction, right? We have some reactants, and this is the real beauty of ultracold chemistry. We can set the exact quantum states of our reactants. We can pick it. How do I want the spin to point? Should it rotate? Should it not? Maybe we give it a vibration. Then something horrible happens at short range. The collision complex. This is where all of the rich dynamics, I say horrible, but fantastic is another way to say it, right? This is where all of the rich dynamics that challenge theorists and computers, this is where it happens. And then at the end, we have some products. And which products we get is going to be controlled by these short-range dynamics. So just to set some scales, right, maybe why ultracold chemistry is a very strange kind of chemistry. Again, I keep trying to make friends with chemists, so wave numbers. Multiply by 30 gigahertz if you need. So our collision energies are microwave numbers, right? The well depth, depending on which potential wells you're looking at, we'll be looking at a couple of different ones, anywhere from 300 to 10,000 wave numbers. And the energy that can be released by different reaction channels, again, is on the scale of 10,000 wave numbers. Okay? So really odd separations of scales going on here. One other picture that I really like for the collision complex is this one from an old paper from John Bone, right? So he's doing a classical trajectory simulation, and a diatomic molecule and an atom come in, and they never come back out again. So this is sort of like a government censorship dot, except it's not. It's just that every point is covered by every one of the particles so many times that when you project it all out, it's just this blob. So we'd like to know what's going on in there. So the first set of reactions that we looked at are reactions between sodium-lithium molecule and a sodium atom. And in the spin polarized states, this is sort of potentially interesting. We hoped it would be interesting because the only possible product that's still spin polarized is at a higher energy. Okay? And I said our collision energies are microwave numbers. There's no way we can get 50 wave numbers of energy to produce that product state. On the other hand, in that collision complex, when things are rattling around for so long, there's some chance, and in fact, most theory results would have suggested anything that is not excluded by symmetries or something, anything that can happen will happen. And so if a spin flips at short range, then we've got all of these great products we can make at dramatically lower energies, okay, really highly exothermic reactions. And so, you know, energetically this could happen. The question was sort of dynamically, can this happen? And this was really sort of our first, you know, can we peel away this dot and see, are these spin flips happening at short range? So what we found was if we created the initial state not perfectly spin polarized, so molecules in the upper stretch state and the atoms in the highest non-stretch state, we have fast loss. And the reaction goes pretty close to the universal rate. But if we straighten out that spin and get perfectly spin polarized, the reaction slows down dramatically. And we see about a factor of 100 change in reaction rate here. In fact, the loss rate is now getting sort of close to what we have when we have just molecules alone. Now, I should mention, these are fermionic molecules, so there's a really strong P-wave suppression of the reaction rates for molecules on their own. And we're seeing that the atoms and molecules are really not that much faster reaction rates. So with that, we said, okay, great. This must mean that we have a lot of elastic collisions, or we hope that means we have a lot of elastic collisions. And if we do, you know, we should be able to sympathetically cool. And so that's what we did. We showed that we could sympathetically cool the molecules with the sodium atoms. So we produced a sample of about 30,000 triplet state sodium-lithium molecules in their row vibrational ground state, and about 300,000 sodium atoms, like 10 times as many sodium atoms. And we can sort of do a number of things. This is the nicest one, cooling them down. But to check that this was not just a fluke, we also parametrically heated the sodium and saw that we could sympathetically heat the molecules. Okay? And so we could extract scattering links and so forth. So we see almost 100 elastic collisions per inelastic collision in these states. And so we were able to cool these guys down, have a phase space density increase of about a factor of 20. That's in this paper in 2020. Okay, so that's all great. That means we've got a reasonably stable system. And if we've got a reasonably stable system, then we wanted to look for Feshbach resonances. In part because, again, a lot of models, you know, this sort of sticky collision models, this type of thinking would say you can't have Feshbach resonances. There's not any kind of coherence at short range because there's instant loss. Well, we don't have instant loss, so maybe we can have coherence at short range. And now I want to sort of talk through a model for Feshbach resonances in these sort of potentially very lossy systems. And first kind of get at the standard wisdom of this universal loss model. Right? So if we've got some molecular potential, things are colliding, I've kind of marked the threshold energy that we're colliding on. Molecular potentials are complicated. This one doesn't look very complicated, well, complicated for me. But we can boil this down to something a bit simpler, which is a pair of mirrors. Right? So at ultra-cold temperatures, most of what goes on when two particles collide is actually quantum reflection on the long-range potential. Right? This is like a pretty good mirror out here. And if they should happen to make it into short range, well, there's a brick wall here. That's a great mirror. So we've got two mirrors for the wave function. And when we think about this universal loss model, the universal loss model says that we expect such strong reactivity at short range that any collision where the particles make it to short range is a loss. Some kind of reaction, relaxation, something like this happens. And so we have 100% loss at short range. And I've marked that by something sort of dirty in the cavity. Don't know what that is, but it's, you know, maybe a fingerprint or something. But so there's something lossy in the cavity, right? So the universal model would say, great, I have some collisional wave function. They're impinging on the long-range potential. There's quantum reflection, so not much of that amplitude actually gets in. And what gets in all gets scattered away, disappears somehow in this smudge, so that it doesn't even know that there's another mirror over here. Right? So we have this loss at short range, which means there's no chance to build up coherence. There's no, you can't know there's a cavity if you can't even get to the second mirror. Right? And so that gives you an expected reaction rate that's purely determined by the long-range potential. Now, what goes further than this is if you have something lossy, but let's say less lossy. Oh, it doesn't come through at all. Extremely non-lossy. So there is a smudge there, but somebody came and did a pretty good job of cleaning it, not completely. So a bit of light is going to scatter out of the cavity, but most of it's going to plow right through there and see that there's a mirror. And so if we're on resonance for this cavity, we're going to see a buildup of amplitude inside, right? So this resonant buildup in the presence of a weak scatterer can actually give you a faster reaction rate. This was the first time you hear this, at least for me, it was very counterintuitive, right? We're going to turn down the loss rate at short range, which means the reaction rate goes up. Okay? And it's this resonant effect. We can build up a huge amplitude at short range that then is scattered away into these reactive channels. Now, similarly, if you aren't on resonance, you can have an incredibly tiny amplitude at short range. So we can actually go both above and below this universal loss model. So that's what it looks like in data. For sodium, lithium plus sodium, because we have this long lifetime, the background loss rate is down here, whereas this universal loss rate prediction is here. And so because we have this low loss rate, we can tune around and we can find these Feshbach resonances, and this sort of is a particularly clean one. This is like a 20 Gauss wide resonance. You can see it's coming up and nearly banging into the unitarity limit, which is the absolute limit for a loss rate. We also have sort of a second little Feshbach resonance hanging out to the side here. Broad, not because it's a strong resonance, but because the underlying bound state has a very short lifetime. Okay. So we see these two very different kinds of Feshbach resonances in relatively close proximity to each other. Now, based on that, and I should say there's also work before this, the first observation of these atom-molecule Feshbach resonances from the Zhao group at USTC in sodium, potassium plus potassium. And so we wrote this up along with this sort of Fabry-Perot model in this paper from 2022. But seeing these two different kinds of resonances gets you to think, well, what else can we learn about reactions by looking at different resonances, their different properties, these sorts of things. But before getting into that, we had one other Feshbach resonance that was exciting to us, which is molecule-molecule Feshbach resonance. Okay? And this was the first Feshbach resonance between ultracold molecules. Again, this was something that was very much expected to not happen. Okay? It should just be total chaos in the collision complex, nothing else comes out. It's actually particularly odd because the background loss rate here is very close to the universal loss rate. Okay. So that model I gave you said, oh, okay, if our absorber at short range is weakly absorbing, then we can start building up some coherence in that cavity. But if your background loss rate is basically the universal value, that should mean you've got about 100% absorption in your cavity. So we had to spend a lot of time thinking about what was going on here, and had some help from Timur Chervil in figuring out just what's happening here. Now, we have a suggestion for what's happening. I don't think any of these people would say we know what happened to make this Feshbach resonance. But one plausible model for this is that you have sort of a side channel in the reaction with a separate set of quantum numbers, and that's sort of a small part of the collision, and it also has some loss rate, but that by tuning the field, what we do is we actually turn that loss process off. So there's this very brief window where you have this picture of a weak absorber in a side channel. We even put together, if you put a beam splitter in your cavity, and so you can make something that works, but it takes a good bit of thought to see how you can have a Feshbach resonance feature in the presence of universal loss background. So now, having seen sort of a lot of different kinds of Feshbach resonances, having to sort of make up stories for how they work. We wanted to go back and look at these sodium lithium plus sodium resonances with a more global picture. Okay, if these are markers of coherence at short range, if we have a lot of them, can we learn something sort of really serious about the short range dynamics? And think of this a bit like, high energy physics experiments, right? You throw a bunch of particles together, bang them around, hope that you learn what's going on by banging them around in different ways. And so we can do this, right? We can look across 1400 Gauss. We can look at different initial hyperfine states. So this was one trace. This is for the upper stretch state that I was talking about earlier. Well, if that works, I wonder if the lower stretch state works. Turns out that works as well. Just to give you a picture here of the hyperfine structure for the molecules and the atoms, and we're looking at sort of these two together up here and these two together down here. Now, one thing to notice is we've got some resonances in the upper stretch state and about twice as many in the lower stretch state. That was a bit surprising. Thought, surely these upper guys want to decay. They've got more energy. And so we got together with a number of theorists, including lots of people who are here, Thijs, Miha, Marcin, and went through what is happening in these reactions. What's happening to give us this particular set of Feshbach resonances. And so I think this is really sort of a realization of something that I had been hoping to see for many years in the course of doing this work, which was that by taking enough data, be strong, keep going, and then feeding it into the right models, that we could actually pull out information about the short range dynamics. So what we see here is comparisons of a bunch of different collision models. Okay? So there's a full model, and the full model gives us a pretty good match to the sort of density of resonances, right? We've got 8 up here, 17 down here, and when we look at blue for the upper stretch state and orange for the lower stretch state, density is, sort of on the right scale. And now what Thijs did was just turn pieces on and off in these calculations and see how do the densities change. And what you can see is, if you take these sort of spin couplings, so there's a reasonably strong spin-spin coupling internal to the molecules, a much weaker spin-rotation coupling. If you take these spin couplings and you sort of divide them by 2, run the calculation, and then multiply the result by 4, you say, if it's perturbative, that should get me back where I started. And sure enough, it pretty well does. Whereas if you take the anisotropy of the interactions, it's sort of the Coulomb-induced anisotropy, and do the same thing, you get this radically different thing than what you had up here. Okay. So what we learned by sort of going back and forth, turning off and turning on, was that there are 2 key aspects to supporting these resonances. One is these spin-spin couplings. They give you the right connections between sort of doublet and quartet potentials, and this anisotropy of the collisions. Absolutely key. Okay, so those 2 together in the short range dynamics give us this Feshbach resonance spectrum. The other thing that was, again, a bit surprising was, why are the lower energy states sort of more lossy? They have more resonances. And the answer is kind of funny. The answer is, well, secretly they don't have more resonances. If you turn off the non-initial Zeeman states, then what you find, we thought, well, maybe that'll put those 2 to the same. The number of resonances in the lower states will go down. No, actually, the number of resonances in the upper state goes up. And it turns out what's really happening here is all of those extra decay channels for the upper stretch state are decaying so quickly that they just broaden away resonances. So there's a set of resonances that we can't see because the spin-spin interaction relaxes them so rapidly. So we really sort of, I feel like we have at least, got a razor blade behind the top of that censorship dot. We're not there all the way, but we haven't voided the warranty yet either, so that's good. So that's sort of the story here, is that by doing a lot of experiments and a lot of calculations and just mashing it all together, we can learn something, I think, pretty profound about the short-range dynamics of this reaction. So I want to show the team here. This slide made a lot more sense when I started making it. We keep collecting up more and more great theory collaborators, and it keeps getting a bit squished, but there they are. I also wanted to show, sort of, Hilma, Julie, and Yukon have all moved on to, less rewarding but maybe more remunerative things in life. And so I wanted to just briefly flash, we do have a new team in the lab working towards the next steps in these experiments. So this is my grad student Paul from Waterloo. Unfortunately, Wolfgang student Hongyan was out sick that week. And then our new postdoc Gary, who just started recently, working towards, adding maybe some new knobs that we can switch on and off to sort of get the next level of information about the short-range experiments, short-range reactions. And this is now customary. I'm going to say, oh, I've got a little time left, so just want to briefly talk about two other things. One is a new collaboration with Dave DeMille at Chicago and the francium team at Triumph. Ultracold molecules are, well, not hard enough, right? What if they were radioactive too? Like, what if somebody only had a 20-minute lifetime? Okay, now we're talking. So this is obviously a very long-term goal to do a search for a nuclear EDM, which is to say, search for a shift moment in the francium silver molecule. Francium 223, because it's got this crazy pear-shaped nucleus that enhances your sensitivity to fundamental physics by like a factor of 1,000. And silver, well, I don't have to tell people in Warsaw, silver is a great thing to make molecules out of. Huge electric dipole moment, which means huge internal field and very little external field required to polarize it. So this is our silver machine that's in the process of being built up at Chicago. The francium MOT has been running at Triumph for over a decade now. And we just made an application and got beam time, so I'm going to be shipping one of my students out to Vancouver, and which is probably a good thing from Waterloo. No, shipping them out to do photo association so we can figure out, is francium going to be okay on its own? And then we'll have to figure out if francium and silver will be okay together. But this is a large collaboration to cover everything we want to do. Researching electric dipoles with radioactive ultracold molecules. You've got to have the right acronym for these things, right? Lots of people working together toward this project in the long run. And the last thing I'd be totally remiss if I didn't mention is my own lab at University of Waterloo, where we're building up a cesium-lithium experiment, in part to be able to continue these sort of ultracold chemistry questions, looking at a molecule that's sort of radically different from sodium-lithium in some respects and almost the same in others, looking at internal versus external density of states and these sorts of questions. And there's the crew happily putting things together at IQC, and we'll let you know when we have molecules. Happy to take questions.
Thank you, Alan. I'm sure there's some questions. If not, I'll start. So what do the chemists say about this?
Well, I've gotten some chemists actually a little bit interested in this. For a while, I was getting responses like, triplet sodium-lithium, is that bound? Yes, it's bound. Yeah, I think in some sense, there's some physical chemists who don't exactly know what to make of where to fit this into their sort of worldview. But on the other hand, they can see that there's potential to learn something interesting about these short-range dynamics, and sort of at ultra-cold temperatures, we just really ramp up the importance of the complex. And I think there's some sense that if we can understand things here in room temperature reactions, there should be something that you can take away from it. Now, what exactly, I don't know, because they still don't talk to me that much, but making inroads.
How will you make the frag molecules?
With tremendous pain, I suppose. Yeah. So yeah, we have sort of a set of steps, right? So the first things that we're working toward is just getting a silver BEC, and then in parallel doing photo association measurements on francium. So we want to figure out what's the ground state scattering length, what do we expect in terms of Feshbach resonances and this sort of thing. We have two different isotopes of silver. so that helps in terms of scattering properties. We only need one of them to work. Triumph can make like a dozen isotopes of francium, but there's only one that has this octupole deformation. So we have one isotope with francium that we have to use, and then with silver we get sort of two chances to have good interspecies scattering. Then we have to pick up the silver machine, bolt it to a beamline so that we can mix francium and silver. We're also sort of working on some plans to be able to make francium offline. Turns out there's actinium-227 decays into francium-223, and then with an oven full of radioactive stuff and some ion optics, you can put the francium and the silver together that way. So like I said, ultracold molecules, it just gets too easy, right? So no, it doesn't. That's a terrible lie. Yeah, that's sort of the plan. Yeah.
Time for a few questions. I can ask one that you probably don't want people to ask, but about the sodium-lithium resonances.
Yes. Resonance.
Resonance, yes.
Yeah, I should have emphasized that because Julie took that data by herself. It's a 30 milligauss wide resonance, and it's the only one over 1400 gauss. Scan the whole thing. Sorry, go ahead.
No, I mean, we can ask many questions, but for example, I mean, you explained how you expect to not see this if the background loss is universal, as you say it is, but you only know the rate is close to the universal rate, right? But it could in principle happen even if the loss is very non-universal. So
yeah, so I mean, this regular, like this sort of standard model that's used for universal loss, this Idzik and Julian paper from 2010. So in that model, you have a single parameter that's sort of what's the deviation from full loss at short range. And that parameter tells you how much you can achieve above universal based on your sort of background loss rate. So yeah, we could say, we haven't calibrated the density carefully enough. Maybe it's 90% of universal or 80% of universal. But in either of those cases, you wouldn't even be able to get a factor of 2 above universal at a Feshbach resonance, right? So, but we're way above that. So there sort of has to be more than what's going on in that model happening here. And that's why sort of our best guess, so I should say, this happens just below a crossing between two asymptotic states. And so that was the cue that made us think, maybe what's going on is in your collision, there's sort of, most of the amplitude goes into one path and a small bit goes into the other. And if that small bit in the other is decaying into this other hyperfine state that crosses just above this resonance, then you could think what's happening is as you get close to that crossing, the phase space available for the decay shrinks, which is to say the loss rate shrinks. And if the loss rate from that channel shrinks, then even if that's, say, 10% of your amplitude, if the loss rate at short range for that amplitude drops to 0.01 or something, you get a huge magnification of that loss rate in that channel. And that's sort of the best model we can come up with. And then it would very rapidly shut off because once you get to that crossing, there's nowhere to decay. Right? So you'd see the loss rate shrinks at short range, and there's a sweet spot where it's shrunk just enough that you get a buildup of amplitude, but there's still a non-zero loss rate that gives you sort of an enhanced reaction rate. And then you get to the crossing, which closes completely. That's the best model that we have. It does actually, that's what these fits are based on. So not totally crazy, but I'm happy to have other people tell me it's crazy or they have a crazier idea.
No one wants to say that. I suggest we thank Alan.